Hello, I'm very sorry I cannot be with you today. As you may have heard, I had an emergency dental surgery last week, so I'm still recovering from that. And also apologies if I'm not speaking very clearly because it's still not great to speak normally. But anyway, I hope that this talk will work. So here I am recording this. So let me share my screen and then we can begin. So you should be able to see my screen, and now I'm going to start the slideshow. So hello again, my name is Urška Demšar. I'm from the University of St. Andrews, and I was invited to give a talk on integrated science of movement, which is a concept that brings together movement research from human mobility and movement ecology. So first, maybe a little bit about me. My original degrees are in mathematics and GI science. But then about 12 years ago, I started working on movement analytics. And the catalyst for this was the cost action move to which I was invited. Now, I'm not sure if you're familiar with cost actions. These are European networks where researchers from all the European countries can join to discuss and work on a particular topic. And MOVE was interesting in this respect because it was unusual. And it was unusual because it didn't just bring researchers working on a particular topic, but it actually brought together methodological researchers, such as people from GI science, computer science, and so on, with people who are actually collecting movement data and who were then interested in a particular aspect of movement. So this was the first time where I actually encountered movement data, and I worked with both human mobility and animal movement researchers. And through the years, these efforts that started as MOVE just expanded in a lot of workshops and a lot of ideas. And one of the things that came through is that there are a lot of similarities across movement research. And so this led to this idea of the integrated science of movement, and I'll talk about that in a moment. So this is what I've been working on in the last years, and also about the story of animal migratory navigation, which again, I'll talk about more later. So what is integrated science of movement? Well, movement data are everywhere. So we are tracking people, we are tracking vehicles, we are tracking animals. People are tracking themselves when they go for a run or bike, like on Strava here and so on. So this has basically now become an integral part of our lives. And what is still lacking, or what is not really following, are the methods for analyzing all this, and there's a need for more methods and better methods to do that. And now I try to put together a overview so that you see that this is actually not something that is so new, because movement analysis has been around for over 100, almost 200 years. So if you, for example, look back at the content disciplines, as I call them, so geography, transportation, and ecology, they all started being interested in movement a long time ago. So for example, the first example of origin destination maps, where you have people going from one location to another, are from the beginning of the 19th century, and ecology started even earlier with bird ringing, when basically you put rings on a bird and then you observe where you find the same bird. And this then continued throughout the 19th and 20th century. So there were methods for analysis of OD flow, spatial interaction modeling, and geography back in the 60s and 70s. And this then increased later on with various topics in human mobility, in geography and transportation. So the two things I want to emphasize here are the transportation four-step model, and I'll talk about that later, and then the cost action move, which started in 2010. So this is where this idea of integrated science of movement started. At the same time, ecology also started way back, as I said, and then back in the 50s, 60s, the VHF radio telemetry basically kicked off most of the modern methods that we now use for analysis of animal movement. And the one thing, again, here that's important is the movement ecology paradigm in 28, when the ecologists basically sat together and came up with an idea of how we can represent animal movement in a conceptual way. What you will also notice from the slide is that all the methodological disciplines, such as computer science, location-based services, physics, and so on, didn't actually do anything about movement for a long time. So not until 2000. And the reason for this was that in 2000, the GPS data became available to the public at the accuracy that was previously only available for military purposes. So at that point, all of these things kicked in, anything from trajectory data mining, visualization, and so on, and physics analysis of complex networks and human mobility. So basically all these disciplines just said, okay, here are all these great new data, so what can we do about it? But what is really missing is the kind of cross awareness of what the others are doing, and also the awareness that if we put things together and we looked at things in a more holistic way, we would be able to find better solutions to movement problems. So through cost activities, after a while, there came this call that we should maybe look at this more holistically and converge research on animal movement ecology and human mobility science. And this was the first paper that called for this in 2019. And basically it asks how we can cross the disciplinary boundaries and raise this awareness. And this paper came up with the idea of a top-down approach, which was based on a series of expert workshops, and it was advocating interdisciplinary collaboration. And this is all, I think this is a great idea. This is something that I think is really needed, but it's still not really working because people are still stuck in their own silos. So if you look at this paper, this just came out like a few weeks ago, 7th of May 2024, and it's a really useful review on mobility data science, except it just ignores that this is done in any other discipline except computer science. So if you read this, it's all computer science. It does not even mention closed disciplines such as GI science or spatial data science, let alone movement ecology. So I think we are really far from this idea that we should build an integrating science of movement. But there are steps that have been taken towards it. And this was our response to this idea that we should just have all these interdisciplinary collaborations to find out what is similar and what is not. But well, we said, okay, but we can't do that unless we know what is similar and what is not. So we can't integrate the concepts if you don't know what everybody's doing and how these things are similar to each other. So we wrote this paper a few years ago, and we study two things in here. We study what is and isn't similar, and we also propose a common unifying paradigm, which is based on principles from animal and human movement. So let's have a look at this paper in the first part of the talk. And the one thing that came out of this is that lots of things are similar, and there's this very basic concept at the bottom of everything, in that movement can be analyzed in two ways. And this is basically reflecting the two philosophical perspectives of movement. So either we have moving objects, which are, for which we then record locations through time. So we get trajectories. So here I have some animal trajectories, here I have some people trajectories, and this is called the Lagrangian analysis. Or we don't have objects, or we don't know the location of objects at all times. What we know is that objects move from one location to another. So we only basically have the origin and destination. And what this builds is then the representation of movement, not as a property of object, but as a property of space. So basically here I have, and this builds basically origin destination flows as well, or they are an example of this. You can have other examples here, but origin destination flows are an example of Eulerian analysis. So basically this is a presentation of how many people move daily from different locations in Scotland. So you have a flow between, let's say, I don't know, Glenrothes and Perth, right? So how many people went from here to here? Or you see this in bike sharing data, or you see it in the data, acoustic data on shark movement. So here we have the receivers around the island, and here we have this flows of the sharks going from one receiver to another in a space-time cube. So this kind of analysis is called Eulerian analysis. And what we tried to do in our paper was to put together the paradigms from movement ecology and from human mobility, and also to put them together for both Lagrangian and Eulerian analysis, because at the moment in movement ecology, we have one very influential paradigm based on Lagrangian analysis. And in human mobility, we have a lot of paradigms that are by either Lagrangian or Eulerian, but they're not very commonly used, except from a very old one, which is actually from 1970s, from transportation analysis, and it's based on Eulerian analysis. So what we did was we basically looked at all this together and tried to come up with a joint paradigm. So to better understand what we did, let's first have a look at the basic paradigms here. So the movement ecology paradigm says that we have the individual. So this is Lagrangian analysis. We're looking at individual objects or individual animals. And we have this individual, and inside this individual, there are several different things that we need to consider. First is the internal state, so why to move. Then we have navigation capacity or where to move, and motion capacity on how to move. And all of these things affect each other, and they're all affected by the external factors. And the movement is basically then the process that takes all of that into account and creates the movement path and this is the path of an individual, so it's a trajectory. And at the same time, in transportation, we have this 4-step model coming from 1970s. And this model basically is built on using the origin destination flows. So we have the flow data between zones in a specific area, and what it does first is it generates the trips from these flows, and then uses spatial interaction modeling to distribute these trips, and then also looks at the mode choice, so how to move and what route to take. So if you look at the questions here, they are same questions or similar questions than the one in this paradigm. And what I also want to say, because there's this table up here, is that in movement ecology, this paradigm is extremely influential. So it was developed in 2008, and basically every movement ecology paper, or almost every movement ecology paper, then references this one. Now, in human mobility, it's a different situation, because there's it seems like there's a new framework or concept or paradigm every year or so. Well, not every year, but there are lots of them, and there are lots of different ones, but none of them is actually so fundamental as the one here, and they just, they don't get cited a lot. So if you look at some of the citations, there's no citations at all. However, the transportation 4-step model is an influential one, but it comes more from transportation than from human mobility. So what we did was we took these two together and built our own model, which includes all of these questions. So questions from both of the models. So we take the animal paradigm, animal movement paradigm as the basis, and then we add the questions and the space from the transportation model. So here we now have the individual, so who is moving, this is the yellow bit, and we have why move, so this is the internal state, the decision-making process, then where to move to, but we also separate this from what route to take, which is which comes from transportation, how to move, and then all of this is affected by external factors and creates the movement pattern, but we also consider what space are we moving in. So is this continuous, discrete, unconstrained, whatever kind of space. So based on this, what we can then do is that we can classify any movement study that we have based on these 6 questions. So here is an example of a table from the paper, and I'm not going to read all this. You could just look it up at the paper, but basically took 4 papers here, 2 from human mobility, 2 from animal movement, and these 2 are Lagrangian and these 2 are Eulerian, and we can just look at all the questions that we set up and basically answer all of them, and this gives you the classification of any kind of movement study. So this was the first part of our paper. In the second part of our paper, which may be more interesting to you as PhD students, and this is, if you're going to read the paper, this is in supplementary information 1. We looked at what are the similarities between methods in both 2 areas. So what we did was we defined tasks for Lagrangian analysis and Eulerian analysis that are commonly performed. So you can see here 7 tasks, Lagrangian analysis, 5 tasks in Eulerian analysis. And for each of these, we basically made an in-depth literature review of methods in both animal movement and human mobility. And again, I'm not going to talk about this because you can just go and read it, and that might actually be useful, more useful than me just explaining all of it. But some lessons that we learned from this process is that there are more similarities than we expected, and there are actually equivalent methods on both sides. They're just called differently. So you may not be aware of what, I don't know, activity space is called in animal movement. But we also found out that movement ecology leans towards statistical methods, but human mobility leans more towards machine learning and data mining. However, what we also found interesting is that there are some tasks where there are no corresponding concepts on the other side. And this is what I want to focus the rest of this talk on. So I want to give you an example of of methods from animal movement that do not exist in human mobility, and then maybe think a bit or consider a bit of how they actually could be used in human mobility. And I'm going to give this in the example of my current project, which is studying migratory navigation. So what we are looking at in this project is how the environmental conditions affect movement decisions during long distance migration. And the 2 methods or methodologies that I will talk about that are not commonly used in human mobility are biased correlated random walks and step selection analysis. So let's have a look at this. So first of all, why studying animal migration, and why is this something that is interesting? So in this video here, I'm showing the data from MoveBank, which is a portal for animal tracking data. And these are real data where you can see animals moving through the year. So now we are in March, and you have this south north movement across the world. And you will see a lot of animals. These are mostly birds, but there are also some sea mammals and so on. So you will see they all just moved up to the north, and these are moving across entire continents and very long distances. And what if you now observe when they're going back, basically you will see that they just take a direction and just fly in that direction or just move in that direction. And they know how to go. So they are like in Siberia, and they just take a track and move to Germany, or they are somewhere like you will see here now in India. Some of them will just basically take a direction across the sea to Africa. It's like, how are they able to do this, right? So this is what it's called true navigation, finding your way to a faraway place using only locally available cues. So basically animals are wherever they are. They look around, they sense the environment, and based on the environment, they determine where they have to go. And I think it's completely fascinating how they are able to do that. And I think, and nobody really understands how this is possible. So, okay, so let's talk a bit of how this is possible, or how navigation works in this respect, or even, well, navigation in general, not just for animals, also for people. So the first thing you need to know is where you are. So if you want to go somewhere, you need to know where you are. And this is called geographic positioning. What this is called then map navigation, and it has been proposed that animals used either visual landmarks, or that they smell their way, that this is like olfactory environment that they look at, or that they use Earth's magnetic field. And then the second thing they need to do is they need to identify in which direction to go, and this is called compass navigation. And it has been shown that they use the sun, stars, or Earth's magnetic field, or even polarized light of the sun. Now, I said it has been shown, but the problem with animals is you can never really know 100% like you can with people, because you can never have like the ground truth if you want. So with people, you can always ask what the basis of their decision was to do something, and with animals, you cannot ask them. So the only way to analyze these kind of things is from the data or from the observations that you have, but you can never actually know that your results are what are the real thing. Now, how is animal navigation studied? And specifically, I'm going to focus on geomagnetic navigation because this is what we've done in our project. So looking at navigation using the Earth's magnetic field. So how is this done traditionally? Where there are lab experiments where they raise animals, birds in this case, in a cage, which is called the Emlen funnel. And then when it's time to migrate, they open the cage and the bird flies into one direction and scratches the funnel in that particular direction. Or, I mean, these days they have computer vision for this. And then that direction is considered to be the migratory direction. And I think this is useful, but it's sort of limited because how do you know that the bird didn't change the direction as soon as it went out of sight? So not a great way to do that. Then more recently, birds have been tracked with GPS trackers and they've been performing also displacement experiments. So this is when you take birds to another location and then you see if they actually compensate for the migratory direction or not. And there have been some simulation studies where they were trying to link tracking data with environmental conditions, in this case, magnetic field. But in these studies only normally consider that magnetic field only changes across space, but not across time. And so in our project, we are trying to, or we are piloting a data-driven approach. So where we are going to reuse open tracking data from many individuals and species, and these data are available through the MoveBank data portal. And also we will use the open environmental data, so in our case, geomagnetic data, to explore what actually happens in the wild. So not just as the bird flies out from the cage, but during the actual migratory trip. And we can do that because we have all this tracking data available. And the other novelty here is that we consider the geomagnetic field changes over space and time. So if you've ever seen, for example, northern lights, so northern lights are basically a visual representation of the magnetic field so northern lights happen when the particles from solar wind enter the atmosphere and they follow the lines of the magnetic field down into the earth. And as they follow these lines, they excite gases which then glow. So this is what you see. So these are the lights that you see. And yes, this changes through time. So here is a video of how this may change. So I'm not sure if you're familiar with the magnetic field, so I thought it might be useful just to give you a short recap on this. So basically the Earth is like a magnet, bipolar magnet. The north pole of the Earth's magnet is on the Earth's south pole, and the south magnetic pole is in the north, but they're not completely aligned with the geographic North Pole and South Pole, so they are a bit of an axis. And so the field then consists of the field lines that start in the North Pole and then go around out of the Earth and then around and back inside. And these lines are have an angle at which they go out of the Earth, and this is called the inclination. And they are also they have different strength of the field at different locations on the line, and this is called the intensity. So if we can represent these lines by measuring the magnetic vector. So these are these green arrows here, and if you look at this magnetic vector at a certain location, you normally observe it in the northeast and center coordinate system. And you, from this vector, so basically you get the measurements of the magnetic field in the northeast and center axis. And from these values, you can then calculate the intensity, which is the length of this vector. You can calculate the inclination, which is the angle between the tangential plane to the surface of the Earth and the actual vector. And you can also calculate the declination, which is the angle between the projection of this vector onto the tangential plane and the geographic north. And you can also calculate the horizontal intensity. So this is h, which is the length of this projection onto the tangential plane. And so these values will change depending on where you are on the Earth. Down here, where the lines go out of the Earth, the inclination is -90, and then here the vector is then parallel, so on this side it's maybe easier to see. And so here the inclination is 0, and then as it goes into the Earth, then the inclination is 90 degrees. And the intensity also varies between about 60,000 nanotesla at both poles and 30,000 nanotesla at the magnetic equator. So this is how it looks in principle, except this is nature, so things are not so simple. So in principle, if the Earth was just floating in space like this with no external effects, this is how it would look like. But the Earth is orbiting around the sun, and so it's not actually in empty space, but it's in this solar space, in the space that is affected by what the sun is doing. And what happens is that the sun also has the magnetic field, and sun keeps sending out particles that bring this magnetic field with them. And as these particles reach the Earth, so the particles are called the solar wind, what they do is they sort of distort this nice bubble that I showed you on the previous slide into something much more irregular. So instead of having two equal sides of this field, this bit here is really compressed. So the side on the solar, sorry, the side of the magnetic field that looks towards the sun is very compressed, and the other one is extended far away. And because the Earth rotates in 12 hours, this bit here becomes this bit here, and then another 12 hours it returns to that. And in addition to this, the solar wind is not regular. You can have a lot of pressure during events such as the explosions of the sun, which create coronal mass ejections. And when that comes, all of this becomes just really, really disturbed. And in that, then what we have is the so-called geomagnetic storms. And this is also when you see the northern lights at low latitudes. So you may remember that last month we actually had one of the largest geomagnetic storms in the last solar cycle, and we saw the northern lights down to the levels of like Texas and the Mediterranean and so on. Apologies. Now, why is this important? Well, the geomagnetic storms are most frequent around the equinoxes, and this is also the times when we have spring and autumn bird migrations. So if the birds are using geomagnetic field for navigation, they can get confused during these storms. And why would that be? Well, this is because if you are looking at like a normal location, so this is actually the photo taken in St. Andrews last month on the 10th of May when we had this big, huge solar storm. We had an amazing northern lights display, and this is actually towards the south, and I've never seen northern lights towards the south before in St. Andrews. But if you look at what happens here is that, so the lines of the lights, the lines that you have here are basically the field lines of the magnetic field. So during a magnetic storm, they go like this, in this direction. And they also, the strength is stronger because of the geomagnetic storm. But in normal conditions, St. Andrews is at about 50 or so magnetic degrees. So the normal conditions, the magnetic field would be something like this. So if the birds are using this information from the magnetic field to navigate, if then this happens, what this means is that they would temporarily think that they are in a different magnetic location. And this is something that we wanted to explore from our data. So are birds actually affected from geomagnetic storms? But how did we do that? So the first thing was that we had to link geomagnetic data to the trajectories of birds, and we developed a tool called MagGeo, which takes satellite data from the swarm satellites of the European Space Agency and uses this data to calculate the accurate values of the magnetic field at each location of each bird's trajectory. Now, this isn't a completely trivial thing to do because, first of all, these are not normal remote sensing data in that they are not like rasters like you have with optical remote sensing or radar remote sensing. They are actually measurements of the magnetic field at the location of where each satellite is. So we have 3D points for these magnetic measurements, and we had to then create interpolation method that was going to take these measurements and put them down onto the surface of the Earth, and at the same time taking into account various geophysical properties of how the magnetic field changes with both elevation and space and time. So I'm not going to talk about this more. There's a paper referenced up there if you want interested in how we did that You can have a look at it. But the important thing is that we had trajectories of the birds annotated with accurate geomagnetic data. And so what we then did was we tested various navigational strategies for both compass navigation and map navigation. So for compass navigation, we looked at two strategies. One is the geomagnetic taxis, or the so-called beaconing, which means that if you're a bird, let's say you're here, you look around and you choose a magnetic property. So in this case, I'm looking at intensity F, and you find where you can see the highest value of intensity. So you look around on the horizon, and this is my highest value in this direction, and then I just fly towards that value. The second navigation strategy we tried was the constant heading, which is that we're not flying towards the highest value, but we keep the equal angle to the highest value. So this is something that if you're a sailor, you will know from sailing. So what you do is you keep the constant angle to a specific point. And then we also used the bigradient, or we tested the bigradient map navigation strategy, which basically means that we were using the intensity and inclination as two coordinates according to which the birds could navigate in the same way as people are using east-west and north-south coordinates in navigation. And we use these two types of methods that are not commonly found in human mobility, and I'm going to talk a bit about each of these two methods now. The first method that I want to talk about are biased correlated random walks, which are basically agent-based models. And agent-based models are used in human mobility, but not this particular type of models. So random walks are based on biology of movement, so they're commonly used in ecology. And so this means that you look at all the locations that you have in trajectories, and you calculate the step length and turning angle for each of these locations, and then you generate a simulated trajectory that draws step length and turning angles of your walks from the actual distributions of the animal, of how the animal moved. What we did in our work is that we added these environmental conditions into how the simulated trajectories were built, and specifically we added the geomagnetic conditions for each location. So, and we were looking at the total intensity F, inclination I, and horizontal intensity. So when we had the bird moving at each time, when we had the location, we then simulated the movement by calculating the step length and the turning angle based on the values of the intensity and inclination. And we used data from greater white-fronted geese in this experiment. Specifically, we had 39 migration flights from 11 individuals over several years, and we were looking at autumn migration. So this is where the birds that nest in Siberia then move down to Germany. And we were looking at how they use these magnetic fields, but we were also looking at what happens during the geomagnetic storms. But I'm not going to talk about that here because that didn't use the method that I'm going to show you. So how did we generate our random walks? So the first step, we simulated trajectories by biasing these walks with magnetic fields. So we did that for each navigational strategy that we were looking at. And I have an example here for the geomagnetic taxis for the total intensity. So if you imagine that you're a bird somewhere here, and then you look at your environment, and what you see is you sense the geomagnetic intensity, and you find out where the largest intensity is. So the taxis navigation strategy means that you're going to fly toward that largest intensity. So when we build the model, at each moment, we then calculated or obtained this value, the surface for intensity, and from this we calculated where the highest intensity is, and then weighted the surface using this location of the highest intensity. So in this case, everything flying every direction in this way would be weighted higher than the ones flying in the opposite direction, because the bird wants to go towards the highest value of the intensity. And this here for comparison is the actual trajectory that the bird took. Now, if you don't bias the random walks, they can go anywhere. So here again, I have the actual trajectory of this bird. And then all the simulations where we did for comparison as the null model here, they don't use any geomagnetic information. And you can see they go all over the place. But if we do use this kind of weighting, then you can see that the trajectories start turning southwards or in the direction that the bird is trying to go. So we did that for all the navigational strategies for all individual birds, and we calculated many simulations. And what we then did is that we compared each of these tracks that we got with the actual trajectory. So each of the black lines we compared with the red line using trajectory similarity measures such as point-wise distance between points and various other things. So again, you can read that in the paper if you're interested. And what we then looked at is which strategies on which values, on which strategies using which geomagnetic values created simulations that were the most similar to the actual trajectories. So again, for all the results, see the paper, but I will just give you one of the more interesting results. So if we took the best 10% of simulations here, and we looked at which geomagnetic values these simulations were based on, and if you have a look at this, most of the best ones, and these are the 3 trajectory similarity measures that we used, and most of the best ones were using either total intensity or horizontal intensity or both. So, but not inclination. So this was an interesting result. So it seems that birds may be using intensity over inclination. Now, why would that be? Well, we were looking at a possible explanation, and we looked at how the intensity actually changes across space. And on average, if you now disregard all of that temporal movement that I was telling you about, but on average, the intensity changes for about 10 nanotesla per kilometer, and inclination changes for about 0.009 degrees per kilometer. And there have actually been experiments which found what is the minimum detection threshold for birds, and for intensity it's 20 nanotesla, and for inclination it's about 1 degree. So if you put these two things together, it means that the bird would have to fly 2 kilometers to sense the change in intensity, and 112 kilometers to sense the change of inclination. So it makes sense that intensity would be favored over inclination, because you don't have to go far until you actually sense the different value of intensity. But for the rest of the results, you can read the paper, it's there, and I will also provide references at the end. The second methodology that is also not commonly used on human mobility, or actually I have never seen it in human mobility, is the so-called step selection analysis. And this in ecology is normally used for analysis of preferences in resource selection. So for example, what kind of habitat or what kind of environmental conditions does each animal prefer as it moves along the surface of the earth. But this is the first time that it has been used for study of navigation. So how does step selection analysis work? Well, if you have the trajectory, so again, I have my bird here. Now these are curlews, because this is the data we used this on. So you have the bird at this particular location, and then you have the trajectory to the next location and the next location and so on. So at each location, you have the actual step. And then what you do is you create simulated steps. So these are here marked with dashed lines, where the bird could have gone starting from this location. And these simulated steps are based again on the properties of movement. And then what you do is that you look at environmental conditions on this step, so the main step, and all the fake steps, right? So the observed steps and all the simulated steps. And then you run a conditional logistic regression to compare the selection of environmental conditions. So what that will tell you is if the bird prefers the conditions, or which of the conditions the bird prefers to select to actually move, rather than those that are in the simulated steps, if it prefers anything, because we don't know, because again, we cannot ask the birds or animals in general what they are doing. So for this, we used migration flights from Eurasian curlews, both in spring and autumn migration. So in spring, they move north. So these are the green lines. And then in the autumn, they move south. And we again had quite a number of years of data to work on this. And again, data were available from MoveBank. So now the interesting thing was, how do we actually assign these magnetic values to the real and simulated steps? And how do we do this for each strategy? So I think this was really innovative, and this is basically what I was really excited about. So I have 4 strategies here. One of them, again, is geomagnetic taxis, the simplest one. So where you are trying to fly towards the lowest or highest value of the geomagnetic variable, right? And so if this is here, so these are the actual steps, this is the actual trajectory of the animal, and this is where it starts, and this is where it wants to go. So this is where it ends up in the end. And so at every step, what we did was we defined the perception circle, which is how far do we think the animal could actually sense the geomagnetic field. And then on this perception circle, we then found the minimum magnetic value and the maximum magnetic value, and we interpolated all the other magnetic values in between on the circle. And so for the actual step, we then assigned the value of the magnetic variable that was on the circle where the actual step intersected the circle, and the same for the random step. So this value here for the actual step, and this value here for the random step. Now this is pretty easy, but for the other strategies, it was a bit more complicated. So for the constant heading, what happens here is that if the bird starts here in the current position, then it has to keep the constant heading to the target position, or it wants to keep the current heading to the target position. And what we then had to do was we had to compare angles, because this is based on angles. This is not based on finding of where the lowest or highest value is, but it's based on the angle between that value and the actual step. So for the actual step, the value that we then used in step selection analysis was the angle between the minimum magnetic value and this actual step, and the same for the random step. So we assign this angle here to the random step. Now, minimum value here, because the picture is shown to for autumn migration, where you are going from north to south, and so you want to fly towards the minimum value. And then we use the same for each of these steps. So at each of the steps, we look at the constant heading, and we assign the difference in the angle between the step and the minimum value. Then we also looked at optimum heading, which is similar to the previous one, but it's just that the heading changes at every location. So instead of having the same direction or considering the same angle all throughout the whole journey, at each location we recalculate this heading, and then that means that we get a different angle to the magnetic minimum or whatever it is. And again, for each step, we assign the difference or the angle between the step and the minimum value. And then for the bigradient map, what we do here is, so again, we have the perceptual circle, and we have now 2 geomagnetic values, because for a bigradient map, if you remember, we need 2 variables to mimic in this north, south, and east-west axis in human navigation. But how do we then assign these values to the actual step? Well, what we do is we actually create a separate 2-dimensional space of just intensity and inclination, and we look at the value of the step in each of these, right? So for example, for this one, we would have the green value for the intensity and the yellow value for the inclination. And this is what we would then assign to this step. So once you do that, you run the conditional logistic regression, and you then get the preference. So it tells you if any animal is actually preferring any of these values, and also how and when does it prefer that. So in our analysis, we then added some additional covariates. First is that we split the data based on time of day. So were birds flying during the day or were they flying during the night? This is because during the day, there is a theory that during the day they use more visual landmarks than during the night, and also they can use the direction of the sun. But at the night, when then they don't see things, it's more likely that they use geomagnetic navigation. And we wanted to see if we can find that in our data. We also divided the data according to the spring and summer migrations because they go in a different direction. And finally, we looked at another covariate, which is the angle between the direction of change of intensity and inclination. And because if this is not large enough, then we cannot have the bigradient navigation. So what is this angle? Well, if you look an average intensity map, so this is how the intensity changes over the surface of the Earth. And if you look at, so we are in this area here. So if you look at the gradient, it kind of changes in this direction, more or less. And if you look at the way inclination changes, here in this area, it looks to change in this direction, more or less, right? But somewhere here, like here, it's changing in this direction, here it's changing in this direction, and so on. So the thing is that if these two directions of change, like the one for inclination and intensity, have I mean, ideally for navigation, you would need them at 90 degrees. Now you don't have them at 90 degrees. Sometimes they are parallel, like I said down here, for example, they are parallel. So in areas where they're parallel, they cannot actually be used because they compress the two-dimensional navigation space into one dimension. So then bigradient navigation is possible. But in our area, it looked more or less okay, but we actually calculated that and we included that in our models just to see if that actually is a factor. So the paper is coming out soon, hopefully, and if you're interested, you can then see the results. But I will just give you some highlights here. So in the same way as with the random walks, we selected the best models. And again, the best models that come out are the ones that use geomagnetic taxes for total intensity. And this makes sense because this is the simplest and most robust strategy that an animal could use for navigation. So it makes sense that this could be something that evolved. All models are performing better during the night and during the day. And in particular, the largest increase in model quality was, again, for geomagnetic taxes for total intensity F. So this, in a way, is the empirical evidence for choosing geomagnetic navigation at night. It's actually the first time that anybody did this in a data-driven approach with real tracking data and real geomagnetic data. And finally, it's also interesting that the models where this angle between the directions of intensity and inclination is more than 45% are performing better. So it seems that this does actually play a big role in the navigation. So this is the second method that is used in animal movement, but it's not used in human mobility. And to finish off, I was actually thinking, would this be useful in human mobility? And in particular, I think the step selection analysis could be done. I was thinking, like, what kind of problem could this solve in human mobility? And I was talking to a friend who is a cyclist, and he was telling me how he selects the routes. And I think this is then perfect for doing that. So what he does is he basically generates a route in Strava the way he wants to cycle, and then it looks at each segment of the route that he gets and looks if it's paved or unpaved. It looks at the traffic volume. So does it have a high traffic volume or low traffic volume? He looks at the gradient, and then often also if it's scenic, not scenic, because he prefers to bike somewhere nice rather than in an industrial area. And then he also looks at the weather forecast in particular and the direction and strength of wind. So that's an important factor in Scotland. And also rainfall, but not so much rainfall because it always rains here anyway. So yeah, then, I mean, obviously he does this manually for his training runs when he's training for races, but this is something that maybe step selection analysis could help with, because you could do the same thing as we did with the bird steps, except you would look at various segments along this route and the actual contemporaneous environmental conditions. And then you would run not a step selection, but a segment selection analysis to identify preferences and find the best possible route. So this is maybe something where we could have this kind of interdisciplinary transfer from ecology to human mobility. And on that note, I will finish this talk. I would just like to thank everybody who was involved in this work. So all my collaborators, all my PhD students and postdocs, and then also everybody who supported this talk. So you can see some of the institutions where we are, where people are located at the bottom of this slide. Finally, I will also provide these slides to the organizers so they can pass them on to you, so you don't just have to watch the recording, you can also look at the slides. And I will also add the list of papers that I cited in this talk so that you have that as well. So thanks again for listening, and I hope this was interesting.